And greetings. Welcome to the Evidence and Reasons for the Christian Faith video channel. I'm Salvador Cordova, your host, and our co-host is Jordan Kareem. This video channel is dedicated to exploring evidence and reasons for the Christian faith, but we particularly serve the graduate science student community, also professors and professional researchers who are Christians and also creationists. I'm an evangelical, mostly Reformed, professing Christian, and I'm a young Earth, young cosmos creationist. I used to be a theistic evolutionist, then an old Earth creationist. And actually, strangely enough, after going to graduate school in physics, I became a young Earth creationist. And I'd like to acknowledge those, our supporters and regular viewers, especially the Christians here. I'd like to just offer a brief prayer for some of them and also the world situation. Heavenly Father, I lift up Schnoil, who's been a regular viewer here, and I lift up his dear mother, whatever her medical conditions are. I also lift up Cindy Lincoln and the challenges she's facing, and I lift up the world, just the geopolitical problems in the world, and who knows what else is going on. And I just thank you that we have this lovely day we could talk about physics and explore this universe. In Jesus' name, amen. Jordan, if you'd like to introduce yourself again.
Sure. I'm Jordan. I am a mechanical and nuclear engineer. I have been for a few years now. I'm an atheist. I used to be a Christian back in the day. I used to be a creationist, in fact. But now I'm an atheist, and I run the Reason to Doubt podcast with my former theologian buddy, Jared. So we cover any topic related to skepticism.
That's fabulous. And I before the show began, I asked Jordan if he would, if it'd be okay, and hopefully he wouldn't be offended that I wanted to just open the meeting with prayer, because there's heavy things on my heart and a lot of the viewers' hearts these days. So thank you very much. Appreciate the courtesy there. Covert Cuttlefish, our resident geologist, is joining us. This is going to be a nerd torture session. And people say, well, what's the point of this? Well, there are other channels on the internet where people just try to get in each other's faces and have debates and try to put the other person down. Shows like this are really just for studying and exploring and researching and being very meticulous. And people might say, well, what's the point, Sal? Being a professional creationist researcher, there's a lot of times we will just explore all sorts of things that we don't know whether it's going to lead anywhere productive. And that might be a little bit of this tonight. So yes, there were only two, by the way, Covert Cuttlefish, you're talking about those jets. The XB-70 was only two of them were ever made. They didn't go into production. The X standing for experimental. And turned out because of the Soviet era surface-to-air missiles, it used to be they thought supersonic bombers would be able to outrun the MiGs, and that was true. They couldn't outrun the SAMs. So as beautiful as those airplanes were, they had the, you know, the change in doctrine and kind of the improving technology. The opponent changed the game. But yes, it was a very beautiful airplane. So thank you. Just for those of you who don't know, before I got into biology, I was a defense contractor, and I worked in the aerospace and defense industry, and then also civil aviation later. How I got in biology is a long story. So tonight we're going to talk about the nuclear physics surrounding radiometric dating. And just one thing that I realized both Jordan and I have in common is, well, sorry to be a little bit political, but you know, the oil industry, foreign oil is often owned and often comes from countries run by tyrants. And 30 years ago, I said, I want some sort of clean energy that didn't involve fossil fuels. And I was exploring all sorts of things. I had been interested in solar, wind, you name it. But always in the back of my mind, because of the Pons and Fleischmann experiment with so-called cold fusion, we don't really know what was going on there. Although we've had good evidence of transmutation now, that's why it's persisted. Very respected chemists around the world are doing this, but we don't have a reaction mechanism well defined. And the physicists will not embrace it until someone has come up with a credible reaction mechanism. So what does this have to do with young Earth creationism? Basically, radiometric dating involves having a parent product and then supposed daughter products. Young Earth creationists have been looking for a mechanism to explain the differing ratios and then come up then with alternative interpretations of that same data and saying, if there's another mechanism that was causal, that was responsible for creating those ratios other than just nuclear decay, then there's an avenue then for young Earth creationism. And when I was in graduate school, I actually did a term paper on that led to one thing after another. And then also when I studied cosmology, and the idea of variable light speed was floated around as a solution to inflation of the Big Bang, I said, okay, every origins model can be on the table. No origins model is more outrageous than another. And so that's kind of, in short, how I became a young Earth creationist. So if I could, Patrick, Jordan, if you have anything to say. I saw someone here, Patrick Barnes. I'd like to highlight him. I've not seen him before. It says here, I found your channel some months ago when you were having some serious problems with a church you've been loyal to for a long time and not treating you well. Oh yeah, I haven't been around since then. I just want to say I hope you're in good, comfortable worship situation now. And don't mean to interrupt the topic, just saw you were live and wanted to offer my best wishes that you're back in fellowship with brothers and sisters in Christ. I've been visiting all of the, thank you very much for your thoughts. I'm still in the thick of things. Lawsuits are live, and I've been threatened with arrest and jail from my own church. And people are suing the dickens out of the leadership for their conduct because the assets are in the 200 million mark range and $250 million expected revenue. So this is a $500 million fight. This isn't about theology, in my opinion. It's about leadership wanting control of this empire. And so some of us are on one side and the other, the others on the other side. And I'm planning to have at least some more shows on this, but then I'm going to be migrating it to another channel, SaveMcLeanBible.org, which has a Save McLean Bible website. So thank you for thinking of me. So, well, we'll just move on here. I was wondering if we could cover a little bit of what we talked about last week, because I'd done some more reading.
Sure.
But did your professors at all talk about cold fusion or the Pons and Fleischmann experiment? I know it was probably negative if they said it.
No, like I said, fusion wasn't really the focus because they're training nuclear engineers to make power, and fusion power doesn't exist. So we talked about fusion, from a kind of physical perspective, but it wasn't the focus. And cold fusion never came up because it's not a realistic method of creating energy.
So let me see if I could pull this up.
There is at least one actual way to do cold fusion, but it's not practical for power generation.
Yeah, we had, and I, for those who were, so this is part 2. We had part 1 earlier last week, same time, same channel. And I promised a lot of things in the video description. We didn't get around to all of them. One of them was pyroelectric fusion. And that'll just take a minute, but this is a good chance to recap because I was looking at alternate mechanisms of changing nuclear structure. So here's one we talked about. This is from Physics World. A natural neutron source. And we talked about how lightning can generate neutrons, but in reading this, it brought back a lot of memories from, let me try to make the font bigger here so everyone can see it. We talked about neutrons from lightning in my graduate paper. And this one actually reflects a big section of my graduate paper, term paper. It said, from laboratory studies, researchers knew that intense electrical discharges through polymer fibers could produce neutrons at 2.45 mega electron volts, probably by deuterium fusion. And there's the formula there. I'm not going to bother reading it. Hence, the first attempts to explain neutron production by lightning focused on fusion. Visible lightning strikes are shown in the third panel of Follow the Leader above. Let's see.
It's that picture with the 3 lightning strikes, that one?
Yep. Yep. Lightning strikes can reach a temperature up to 30,000 Kelvin, but it was assumed that this would, in combination with natural deuterium and water vapor, do the trick. This theory dominated the literature for a long time, even though a number of independent measurements proved otherwise. The problem was that if one excludes deuterium fusion as a neutron source, one has to explain what is providing the energy to release neutrons from the nuclei of typical air molecules. For nitrogen, the binding energy is 10.5 mega electron volts, while for oxygen, it is 15.6 mega electron volts. Hints for a completely different and correct explanation came from far outside the laboratory. Since the 1960s, satellites with nuclear test ban treaties here on Earth, later similar spacecraft were launched that used gamma ray flashes to study the cosmic realm. In 1993, however, more sensitive detectors recorded gamma ray flashes coming from Earth that had nothing to do with weapons. These so-called terrestrial gamma ray flashes are microsecond to millisecond long pulses of photons up to 40 mega electron volts of energy. See gamma ray and neutron generation map. And in 1996, it was found that TGFs, terrestrial gamma ray flashes, can be related to individual lightning strokes. And I'll just pause there. So
people understand the talk about binding energy, but it's the amount of energy you'd need to hit the nucleus with in order to knock pieces off, basically.
And actually, this is really all new to me. I could tell, Jordan, you probably work with binding energy a lot, because I had to spend hours just like trying to wrap my head about all the ranges of energy. So I might have to. Could you help me do some Googling, Jordan?
Sure.
Are you set up for that? Can you find out? Can you find out the energy of a photon of light, visible light?
A visible light? Sure.
Okay.
So energy is going to be related to wavelength, right? So the higher energy a photon is, the less the shorter its wavelength is going to be. So at the low end, you're going to have like infrared and even more red than that. Then you have visible light. Then it goes ultraviolet, X-ray, onto gamma rays. So the more energy, lower wavelength. Energy of
So gamma rays.
Photons. Gamma rays are extremely high. So according to Google, photon energy of visible light ranges from 2 to basically 2.5 electron volts. An electron volts is a very small unit of energy. It relates to the voltage for an electron. Just doesn't really matter what it is. It's just a unit of energy, which is some extremely small fraction of a joule.
Right. So a watt set. So when you run your light bulb if you have a 100-watt light bulb,
that's 100 joules per second.
Right, 100 joules per second. And so you could figure out the max, given you can convert joules into electron volts. A joule is a huge number of electron volts. So
a joule is 6.2 times 10 to the 18th electron volts. So a lot of electron volts. Great many.
So I would just guess from the numbers you gave, just the rough order of magnitude, and someone in the chat can correct me. So when you run your 100-watt light bulb, you're emitting 10 to the 8 on the order of 10 to the 18th.
Probably 10
photons.
to the 19th, 10 to the 20th of electron volts worth of. Well, that's how much energy is going into it to run, right?
Right. So it's maybe 25% efficiency, but it would be on that order.
Yeah,
you're
somewhere in that
generating
area.
You're generating a lot of photons.
A lot of those photons are actually in the infrared range, which is why your light bulb, if it's an old incandescent bulb, which is why it got hot.
Yes. Yeah.
Okay.
So 2 electron volts, and then X-rays are higher, and then the gamma rays are the mega electron volts. Now, I looked this up yesterday. The super colliders are in the giga and tera electron volts.
Yes, and the reason for that is actually kind of cool. So when you accelerate something like a photon or an electron, its wavelength gets smaller, right? And the wavelength determines what it can interact with. Okay, so the wavelength needs to be about the size of the thing it's hitting in order to hit it. So if your wavelength is too big, for instance, like visible light won't necessarily hit like the nucleus of an atom. But if you get light that has a small enough wavelength, so high enough energy, then it'll pierce through the electrons and hit the nucleus because its wavelength is small enough. Well, the smaller wavelength you get, so the more powerful your light is, it can hit subatomic particles and go even deeper, like right? So you can probe deeper into the nuclei, like you can probe basically like deeper physics with higher energy interactions, which is why they're always trying to build a bigger and bigger particle accelerator. There's of course like a practical limit. Like in order to test like string theory, you'd need enough energy, like stars. You need like a star level amount of energy, like literally a like a cosmic level of energy. It's a lot. It exists. It is a finite amount. So hypothetically, if we were like a type 3 civilization, maybe we could do it. But you'd need like a particle accelerator the size of the solar system to do it.
Yeah. Well, I had a boss who first time said, well, physicists have been suggesting we have an accelerator that can kind of orbit the Earth, so to speak. It'd be like like instead of Saturn's ring, it'd be an accelerator.
Right.
And I'm like, yeah, in your dreams, buddy. That's not going to happen anytime soon.
Would be cool, though.
It would have been really cool. So I just thought it was interesting that they're conceiving of these things. So just as a passing note, there was a big lawsuit, not a big, it was a significant lawsuit trying to shut down the super collider because there's according to, depending on what theory one had about particle physics, there was a non-zero probability that they could start a reaction that could end the world. And
yeah, I believe it was by spawning a black hole, a baby black hole. And if that black hole, before it radiated away and disappeared, because black holes do radiate energy, but before that happened, if it lived long enough to start hitting, to like gobbling up atoms, then it might not radiate away, and it would like go to the center of the Earth and then eventually grow and like consume the Earth. And I guess that was the fear.
Yeah, there was another one to deal with strangelets. So I just thought that was really funny. And people were saying, well, okay, even if the probability is really low, but the stakes are so high, you don't want to be doing this. So there really was a lawsuit. That's why it made the news, because they were trying. Some scientists were saying you got to stop this experiment. It's too, the risk reward ratio was just not favorable in their opinion. But anyway,
we're all going to die anyway. Why not?
Yeah.
Forward science.
Yeah, science. Okay, so at the time, so this article I read from Physics World just now, that was 2017. When I wrote my graduate term paper, I actually thought this was fusion possibly. And there were papers that were saying this is definitely fusion. But it's just amazing that all the calculations in peer-reviewed papers that said this is definitely fusion was overturned. But
so science works.
Yeah, by this photonuclear process. And I'm interested, I know it's crank or whatever, but for the sake of renewable energy, I am interested in low energy nuclear reactions. That's very controversial. That's a better name, I think, than being called cold fusion, because fusion usually will emit gamma rays, and they have not had an explanation for the absence of gamma rays in these low energy experiments. We have,
I mean, my explanation would be it's not fusion. That'd be
right. I would say it's not fusion, and there was like the Widom-Larsen theory that tried to explain it without fusion. And the lightning, they tried to explain the lightning strikes neutron generations with their theory, and it got superseded by this photonuclear process. Now, the photonuclear process does involve high energy, and
because you need a high energy photon. It needs to have high enough energy, basically, to rip a neutron or whatever off of the nucleus. Because there's a certain amount of energy, just like chemical bonds, you need a certain amount of energy to break the bond. Same kind of thing, except for a neutron. And it's not a chemical bond, obviously, but.
Okay, so I'm just saying that, I think the world for nuclear science, and even just from the engineering perspective, a lot of nuclear physics is oriented for kind of the theoretical stuff, all the stuff surrounding the colliders and elementary particles and the origin of the universe. But I think there's a ripe amount of opportunity for engineering, and we don't know exactly where there's leading. Obviously, for energy, but I think there could be some really just cool devices. And one of them that I studied for my graduate term paper was pyroelectric fusion. Have you heard of that?
Yeah, I've heard of it. My understanding is it's mainly used as a source of neutrons.
Right.
Yeah.
There's the device right there. It doesn't look very big. Pyroelectric fusion refers to the technique of using pyroelectric crystals to generate high-strength electrostatic fields to accelerate deuterium ions, tritium might also be used someday, into a metal hydride target containing deuterium or tritium with sufficient kinetic energy to cause these ions to undergo nuclear fusion. It was reported in April 2005 by a team at UCLA. Scientists used a pyroelectric crystal heated from -34 to 7 degrees Celsius, combined with a tungsten needle to produce an electric field of about 25 gigavolts per meter to ionize and accelerate deuterium nuclei into an yttrium deuteride target. Though the energy of the deuterium ions generated by the crystal has not been directly measured, the authors used 100 kiloelectron volts, a temperature about 10 to the 9th Kelvin, as an estimate in their modeling. At these energy levels, 2 deuterium nuclei can fuse to produce helium-3 nucleus, a 2.45 mega electron volt neutron, and bremsstrahlung, which I believe are gamma rays from decelerating charges.
That's right.
Okay. Although it makes a useful neutron generator, the apparatus is not intended for power generation, since it requires far more energy than it produces. So, again, I thought that was just very interesting.
It's pretty cool.
There is a data point that just struck me here, and since you're into fission, you probably understand this. A 2.45 mega electron volt neutron, I think that'd blow apart a nucleus. It wouldn't cause fission if you had uranium. You need slow neutrons. You don't want neutrons that are moving too fast.
Yeah, but for a different reason. You're not. So a neutron that's doing fission isn't doing the same thing that a high energy gamma ray is for the photonuclear thing. So basically, for that, it's like an impact, like a scattering impact. Well, it's not scattering, but it hits the nucleus with high enough energy to basically break apart part of the nucleus. With absorbing a thermal neutron, it's not like impacting the nucleus and like blowing things up. It's a reaction that can occur where the nucleus absorbs a neutron and that causes it to then fission. And
Right.
That reaction is more likely with a slow neutron than a fast one.
Right. So, I mean, I wouldn't, okay. I finally figured out why they call it thermal neutrons. I had to look it up.
Yeah. Because it's like the velocity of a neutron at like a certain temperature.
Right. Because that, I believe it, I think it's like the mean, I think it's related to the mean velocity. You know, the the particles
20,
have, according to
2,200 meters per second, I think, is the velocity of a thermal neutron, quoting from memory.
So we could work out how much energy is there in terms of electron volts.
Right.
That would be a nice exam question.
The point is, yeah, it's not about the energy of the neutron in the sense of colliding with a nucleus in order to kick off fusion. And also, you can have fast neutrons that also do fusion. Or sorry, not fusion, fission. But it's the same thing. They're not blasting into the nucleus and like blowing it into two pieces. That's not what's happening.
It actually has to join. Yeah. So this very high energy neutron, that's always what amazing. And this will actually relate to our carbon-14 discussion. That we want thermal neutrons. If we're trying to, if like say there's a uranium decay chain that produces, there's a decay chain that's somewhere down in the line of all its daughter products. There'll be a neutron there. It has to be a slow neutron, a thermalized neutron.
Has to be is probably too strong a word, but many neutron absorption reactions work better with thermalized neutrons.
Okay, thank you.
Thank
you for that.
Not all of them, but many of them.
Okay, so all this to point out that, and I was just running through this. I said, and this is just like I read this like just as in like right now, the lightning strike creating 2.5 mega electron volt neutrons. That means that would translate into a certain speed. So you take the mass of the neutron. I don't know if you can use the classical 1/2 mv squared, where you multiply the mass of the neutron by the velocity squared.
According to Google, the energy of a thermal neutron is about 0.025 electron volts.
I'm sorry to laugh. That is so much smaller than the one that's caused by lightning.
Oh yeah, yeah. If you get a neutron flying off from fission or fusion, it is not a thermal neutron. It's a very, very fast neutron.
Right.
Yeah.
So the interesting question is, in a fission reaction, you still need to be able to generate slow neutrons.
Well, that's
fissions.
So that's why you have a moderator in a nuclear reactor. So in a thermal nuclear reactor, which most modern reactors are thermal, like just some Gen 4s are fast reactors, but in a thermal reactor, you have what's called a moderator, and that's a material that doesn't absorb neutrons readily, and instead the neutrons bounce around and lose energy. So that process of losing energy is called moderation, and that thermalizes your neutrons.
So I heard cadmium stops neutrons. Is that correct? Is that what they use to stop neutrons?
Honestly, I don't remember.
Okay.
Good moderators tend to be things with small. You want a atomic number not very far removed. So as a general rule of thumb, you want an atomic number that's low, because if you have two particles that are about the same size, they'll bounce and they'll kind of lose energy, and there'll be an energy exchange. Whereas if you had a very massive atom and the neutron, it would be more elastic. Inelastic.
Exactly.
Inelastic is where it doesn't lose. Yeah. So it hit and would like bounce off and not really slow down. So hydrogen is can be a good moderator, but it's not practical for good reasons, because it's exploding and also it leaks out and stuff. So actual good moderators are water, because of the hydrogen that's in water. That's the usual moderator, because you can use it as a coolant as well. Graphite is another good moderator.
Oh, yes, graphite.
Yeah, but
I remember
they basically
the first nuclear reactor had graphite, I think.
Yeah, they basically use a material that won't absorb, isn't a neutron poison. It won't absorb neutrons, but it scatters them to slow the neutrons down, to thermalize them. Now, you can have reactors that don't use a moderator. They're fast reactors that you would use for other reasons. I would be happy to go into, but it's probably off topic. But yeah, if you want to thermalize your neutrons, you're ideally going to have a moderator.
Okay, so just a brief question. We have Dustin Buck here. How do we know decay rates have always been consistent?
That is a great question, Dustin.
And that's probably this is the topic of the whole series, actually. I would say this, even as young Earth creationists, there are conditions where we would expect it to be consistent and it would be desirable. So I don't think we can change it a little bit depending on the kind of decay. There's some decays we can't expect it to change. And so I would say, as a rule of thumb, I'd say it's constant. But Jordan, go ahead. You're the nuclear.
So you have to remember what is going on with nuclear decay. First of all, it's happening outside of electron capture and kind of those sorts of decay modes. It's all happening within the nucleus. And so just looking at it from a physical perspective, the nucleus is extremely well insulated from its environment, because it's got all of these electrons between it and the outside world. For a heavy atom like uranium, if it has 92 protons, right? So that means 92 electrons. That is a lot of electrons for a sense of scale. If you had a hydrogen atom, so like just a proton and just an electron, that's all it is. and you had the nucleus, the proton, in the middle of a football field, the nearest electron would be miles away. Like it's a huge amount of space from the perspective of the nucleus, right? And so all of your chemical interactions and stuff are all mediated by electrons. And so that's why these processes aren't typically affected by the environment, because the nucleus is so well insulated from its environment. There are some exceptions like electron capture and things like that, but just conceptually that makes sense. So how do we, but even though it makes sense conceptually, how do we know? Well, first of all, we've never measured any change, and it would be awesome if we could change decay rates, but high energy, low energy, high temperature, low temperature, extremely high pressure, no high pressure, nothing seems to affect it with any meaningful amount. Again, and I'm going to stop saying this now, but again, outside of a few exceptions. Beyond that, if they were to change significantly, that has implications, because the decay rate is the same as the radioactivity. There are different ways of talking about the same thing. If something decays faster, that means it's more radioactive at any one point, right? And so if you want to speed up the addition to all the other crazy stuff you're going to have to do, because you're going to have to deal with the fine structure constant and like the strong and weak nuclear forces, and like lots of crazy stuff is going to happen. But if somehow you can manage to get all that to work out, you've still then made everything, or whatever you're increasing the decay rate at least, way more radioactive than it would have been otherwise. So for example, the common young earth creationist idea that I hear most often is that the decay rates were sped up during Noah's flood because of the cataclysm or whatever. Well, if you're going to speed up 2 billion years of radiation into 1 year, that means you're giving off 2 billion years of both radiation and heat in 1 year. That is a lot of radiation and heat. To give you an idea of how much, bread would be radioactive enough to kill you.
Yep.
Like it's the potassium 40 in your bloodstream would boil all your blood. Like it's mind-boggling the level of heat and radiation that would be released. So that doesn't work. Now, some other thing, like if you had like, maybe not everything increases, but maybe for some reason only this one isotope increases its decay rate. Maybe, but that's
right. And I want to concur. I'm a young earth creationist, and I hear this stuff. And the potassium 40 problem was something the young earth creationists themselves pointed out in the rate book. And so there were some nuclear physicists in the gang that said, including Eugene Chafin, Don DeYoung's also a nuclear physicist, they said, this is going to be problematic. So you can say, okay, this solves one young earth problem with the radiometric dating, but then you create both a heat problem and then the potassium 40 in your body basically causing you to incinerate or whatever, your blood to boil.
Yeah.
And I'm just like, okay, why is this not talked about? And I hear this on the YouTube channels and they just sort of dismiss it. And they said, we're working on it. I'm just like, maybe it's the wrong thing, guys. And I was at an international creation conference, and Russell Humphreys, God bless him, he's a good friend. He's contributed to creationism. I said, Dr. Humphreys, there's a problem with heat. He said the white hole cosmology thing might solve that. Well, another physicist said, well, white hole cosmology doesn't work anyway. That was P.W. Dennis. So, okay, it's actually nice to have young earth creationists criticizing each other and trying to correct each other. But the YouTube sphere, and then also the popular, what I call popular creationism that asks for lots of donations, they cover stuff up, and I don't like that. This channel is not about trying to hide inconvenient facts. So yeah, I'm publicly agreeing with Jordan here about the potassium 40 thing. It's not Jordan or the atheist, it's certain young earth creationists that actually know nuclear physics.
Snelling, who was part of the rate project, credit where it's due, he, even as they were pursuing this thing, which I think their premise is flawed, but they, in their papers, identified the heat problem. And I've run the numbers myself, and their numbers are pretty close. I mean, I get slightly different numbers, but I mean, when you're talking about melting the Earth, what's an order of magnitude between trends, right? You know?
Yeah, you don't even need to melt the Earth. You can make it inhabitable. Right. So for those watching, it's like, well, why am I covering all this stuff about photonuclear processes or low energy nuclear reactions? I think for young Earth creationism to move forward, they have to look at low energy nuclear reactions, transmutations. So we have at least one mechanism that can do transmutations, and that's lightning. But I'm not convinced that that's exactly what will alter uh, like radioisotopes. And then one young Earth model has said Noah's flood might have actually created radioisotopes. And I think that that is a compelling possibility. But this is so early in the game, guys.
Well,
And we're not going to move forward if we keep being in denial of the problems like what Jordan and actually other young Earth creationists have pointed out.
the problem with that, though, is like the hydroplate theory is one of those that says like radioactive isotopes were created during the flood, right? By the vibrating plates and the piezoelectric effect. But regardless of what effect you want, whatever, if you want to say that your radioisotopes were created during the flood, you have to say that they were created, the radioisotopes on Earth were created during the flood, because we know that very distant stars have uranium in them.
Right.
And so clearly vibrating plates on Earth have no way to affect a star light years away. So you have to then say, well, those distant stars have had radioisotopes the whole time, but for some reason, Earth didn't. And then the ones we see on Earth were created during the flood. And that's just another level that you have to
Right.
bake that into your model somehow.
Right. And that's an interesting point. It would not have occurred to me to think about this, but and I shared this last week. There's 70 times more uranium in the continental crust than on the seafloor. The seafloor being a proxy of maybe what's in the mantle.
Mm-hmm.
So that really did catch my attention there. And then also the nucleosynthesis problem is it's not trivial. And I'd studied cosmology, and I said, this. I'm not the only one that has said that the uranium appearing on the crust is problematic. This wasn't a young Earth creationist thing. This is something that the people that study planetary, Earth origins has been saying, okay, because we have 70 times more uranium on the continental crust, we need a special mechanism. Okay, if we had a stellar origin of it, like you said here, the Earth had to form from a nebula that didn't have as much uranium, and then it got sprinkled, but somehow it ended up on the continental crust. We can't explain why it's not on the seafloor.
I'm not a geologist, so I have no idea. My completely, absolutely uninformed opinion, guess, would be, I don't know, maybe there's some kind of preferential sorting, and maybe right. Because you're right, but I'm not a geologist. I have no clue. I'm a drooling idiot when it comes to geology. Dr. Dan, Creation Myths, did point out a great thing that I should have mentioned, because it's my favorite thing ever. How do we know constant decay rates? Oklo, yeah. So the Oklo phenomena, because of the prevalence, the different prevalences of the decay products after fission, if things like the fine structure constant or stuff like that, stuff that you would expect would change if decay constants had changed, if those were significantly different, we would observe different things from Oklo, right? And so that also puts a cap or a restraint on how much those things could have changed. So speeding up the decay increases heat by increasing friction by the atomic action between the electron, or more like a hammer pounding on steel will get hot over time. Okay, so when a atom decays, it releases some decay product, which has an energy, because it's moving at some kind of velocity, and that energy is going to get translated into heat as it bounces around and interacts with matter. Okay, and so you can think of it as releasing heat directly. That's basically what happens. So when uranium fissions, that's why we use uranium to heat water to make electricity, because that fission produces heat. The reason it produces heat is because of the mass defect, which we talked about last time. So I can say it again, but you can go back and look up mass defect if you want. Basically, some of the mass gets translated into energy. Okay, And so that happens every decay. There's a certain amount of energy that's going to be released depending on the type of decay and other factors. And so if you say the decay is going to release, I don't know, 10 megaelectron, that's a lot, 5 megaelectron volts for a fission or something, right? If you do so over 2 billion years, you'd have however many megaelectron volts or joules of energy. So that amount of energy got released. Whenever it got released because we have this much decay. This much decay correlates with this much energy because every decay has so much energy associated with it. And so if you compress all that energy up, like if you compress all those decays to 1 year, you still have the same amount of heat that's getting released because every single decay releases energy. So it's not that it's increasing like friction or like it's moving faster like a belt. It's because every time you the atom splits apart, it's emitting heat. And so if you want to have more disintegrations, that's more heat.
Okay, so before we move on, I'm just highlighting this. We're not going to talk about potassium Oregon today. I don't mean to run this off, but I had certain things on the docket I wanted to talk about, but this will be discussed later. We're just walking through this. So Dr. Dan, I think there's a different explanation for Oklo, but I just want to state my position again. I'm in agreement with Jordan that changing nuclear decay rates is bad. It'll cause problems for a young Earth model, heat, and then the potassium-40, which will cause your blood to boil. And as Jordan said, even a slice of bread would kill you at that point if you had accelerated decay. Totally agree with that, because young Earth creationists were the ones who pointed it out. And there's probably a minority in the young Earth creationist community, myself included, that says we need to drop this argument. It's not working. It's not helping us. So my line of attack has been alternative transmutations. One of the mutations I pointed out, mutations in terms of the nuclear nucleus, the atomic nucleus, not DNA. Okay, we can change. It's kind of like alchemy. And one example was was lightning strikes that create photonuclear processes. It's not fusion or fission. It is just a high energy gamma ray that's triggered by electricity. And I've been keeping my eye on low energy nuclear reactions. We don't know the mechanism yet, but that would, because it has relevance to renewable energy, where we could stop using fossil fuels and stop financing tyrants like Putin.
And just stop polluting would be great.
Stop polluting. I'm interested in low energy nuclear reactions, and it could also solve young Earth problems. So it's like killing two birds with one stone. I'm not saying that we've worked it out, but I'm just saying, guys, this is exciting if you can get it to work. And we've had what I consider now, after 30 years, very good evidence we've had transmutations. We've just not been able to figure out the mechanism.
You mentioned, so Testament asked about potassium argon dating. I can respond to that very quickly, or I can answer it later if you want. It's a pretty simple answer.
Later.
Okay.
How about a quick one since he's here? It's great that he's having interest in this. So, and then we'll cover it more because it is an important topic.
15 to 20-second answer is there's going to be error in any kind of method. There's going to be inherited argon and things like that, even with a very new volcano. So that is going to be a static amount of error. So if you inherited, say, 100,000 years of argon, that's not very much argon, because that dating method is usually dating things like millions and billions of years old. If you have 100,000 years of air on a billion-year-old sample, it doesn't matter. So it's kind of like you said, well, I sprinkled a little bit of salt on a truck scale. How come it's not working? You're just using the wrong tool. There's your 15-second answer.
Yeah, I appreciate the interest here, and we're going to try to take some time for the audience, because we're, after all, trying to serve the audience here. But I'd say in both our last show and this show, Jordan and I have had a lot of agreement. So you will not hear me agreeing with other young Earth creationists about accelerated decay. It's like, don't go there. So Erica will hammer the young Earth creationists over that, and I'll say she's right. She's right. Erica's right. Jordan's right. I think I'm right. That's why I'm agreeing with them. And young Earth there have been a minority of it, and it's just amazing how I call it like a bad meme that seems to help keep the interest, keeps floating around because, well, it helps people believe. And it's like, well, you want them to believe for the right reasons. It's better to say we don't know than to say something that is really on shaky ground. And,
Amen.
Yeah. So I know it's just a human tendency. It's like, why don't you have a show that tells us, tells us what the solution is? It's like, I think you're going to have to just say there's no solution right now. And that's hard to live with. I'd rather tell you we don't have a solution than to make up a solution I know would bother my conscience. Okay. So I know that's not satisfying, but that's where I am. So, okay, why would I believe still in young Earth creationism? It's because, ironically, of radiometric dating. It is specifically carbon-14. And so this is going to be a contentious discussion here, but we'll just try to go through this methodically. So, Jordan, you've heard about carbon-14 in coals and dinosaur bones. So
Diamonds.
In diamonds.
Mm-hmm.
All right. So we're going to cover a little bit of a paper on that, and I wanted to hear what the explanations you find for that you find credible.
Well, for some of them, the explanation is as simple as experimental error. Often, when it comes to things like diamonds, usually the ages for the carbon-14 ages they find are in the 50,000 range, which is right at the very threshold of detection and like beyond being able to differentiate between air and background and stuff. And so when you start quoting ages that are like in the 45 to 50,000 range, it's hard to say for sure whether that is significant outside of the air, when it comes to, so that's like the dinosaur bone, or that's like the diamond one usually. Another possible explanation is de novo production from neutron flux or from the decay of radioactive isotopes in the ground. So other sources of carbon-14. And that seems a bit more plausible when it comes to coal and stuff. But there you go.
Okay, so I'm going to give my perspective on that, and I'm going to transfer a file here that has. First off, I wanted to talk about the background thing, and I don't multitask well, so I'm going to. I'm trying to transfer a file that shows accelerator mass spectrometry. I'm going to contend that this whole thing that they're saying that it's background, I don't think that that's correct.
Well,
it depends on your measurement method, first off.
So background or other sources of error, because there's always going to be error. No measurement is ever 100% accurate. No matter how careful you are, it's impossible.
Okay, so let's see. I had a video on the accelerator mass spectrometry machine, and I've lost it. I feel really dumb now. Do I have the I really wanted to show it, and if I don't, I feel really bad now. Oh, okay, here it is. I have to transfer it to my thumb drive here, and I'm going to put it on my other computer. So if you had anything else, could you, you said there was another thing as far as de novo production. So what explanation have you had for that?
So basically, the idea is that you could have carbon-14 production because of a neutron source of some sort in the ground with the mineral. So carbon-14 can be produced if carbon-13 absorbs a neutron, or if nitrogen-14 absorbs a neutron, or if they absorb a neutron and the neutron could come from spontaneous fission, or maybe, I don't know, some kind of photonuclear effect or something. And so it's conceivable, at least, that you could have a source. So basically, the reason carbon dating is used is because the atmosphere has some level of radioactive carbon. And so the age that you get is kind of assuming that the carbon-14 content that you're seeing is from the atmosphere originally. And so the thing is breathing in carbon-14, it dies, it stops breathing, so it's not getting any more carbon-14, and that carbon-14 decays off over time. And so kind of naively, if you looked at like coal, which is millions of years old, there shouldn't be any carbon-14, right? Because the stuff was breathing on the surface and it died, and then it got buried, no exchange to the atmosphere anymore. So why is there carbon-14? That's where the de novo generation could be a possible explanation.
Okay, so what I've said here, this show is not about arguing and trying to put down another person like a lot of other channels. I say the way we could resolve the disagreement is we can propose what sort of experiments need to be done and what outcome would then help us come closer to both sides agreeing that this is the answer. Mm-hmm. So one thing I'll mention is contamination is another issue. Mm. Contamination, and I was just thinking about this. I said, okay, so we've been carbon dating primate bones, because human evolution's of interest. And I said, well, how do you know contamination isn't in play there? Because we, and we can compare the protocols. But
it almost certainly is.
Yeah. So before we go any further, let me just show there are two ways we can detect. Let me see if let me show this one here. We can detect carbon-14. There's one that's not too expensive. It's not very sophisticated. It's using just a plain old Geiger counter. If you have I heard that's one way to detect it. I don't know how you have to prepare the sample so that you can, but I presume like if you can chemically extract all the carbon or whatever, you can use a Geiger counter, but it's limited to how far the dates. After more than about 30,000 years, you do have to deal with cosmic background radiation as a problem, because your Geiger counter could be picking up stuff from all over the place. So the word background radiation, I still see some anti-creationist articles that will refer to that, and that was before the advent of accelerator mass spectrometry. So let me show you, I got the copyright clearance on this one, so I'm going to play it just for the benefit of the audience, and I think this is really cool because you'll hear from me referring to this, and I will argue that there's good reason to accept the figures. I mean, it's a very good technology. And so when you get to the 50,000 year mark, we'll talk about that a little more. But in the meantime, let me roll this. And I'm going to mute our microphones here, Jordan. I'll turn it back on when we're done with the video, just so we get better audio quality.
The AMS itself, an accelerator mass spectrometer, has really three components. One is called the low energy end. Let's take the example of carbon. And radiocarbon is present in the environment at 1 million millionths of an atom. So it's a very, very trace isotope. So what we do is we take any sample, we convert it to graphite. There's a little aluminum button with the graphite in the center of it, and we can mount up to 200 of these graphite targets into a cartridge type, we call an ion source. Because what we're going to do is take the atoms of carbon in that graphite and convert them to ions. We're going to ionize them. Once you get things ionized, you can move them because we use electrical fields and voltage fields, voltage gradients, magnetic fields to move these ions around. So we're going to create an ion beam. So it's a beam of carbon racing out of our source. We bend that beam around with magnets and electrostatic devices, and aim it into a big tank. So we're looking at a tank right here. It's a T-shaped tank filled with an insulant, sulfur hexafluoride, because we're going to create a huge voltage in that tank. And so it's like a big transformer that you see in hydro systems, except ours is 3 million volts. So we're going to race those ions towards that positive pole, and then we're going to switch them. We're going to strip those electrons off carbon and turn it to a positive ion just as it hits that positive pole, and it's going to shoot them out the other end. Now we're going up to a few percent of the speed of light. So our ion beam is really rocketing as we're walking over here now to the west side of the machine. We're at the high energy end. So our ion beam is racing out as the flight path goes into a magnet. And we've got a few control sensors along it. These are electronic lenses, so we can change the shape of that beam. So now we're looking at a magnet. It's actually the big, what we call the analyzer magnet. It's 18 tons, a whack of energy, because we have to bend that beam at 90 degrees. And so we've got just pure carbon coming down there, but carbon has these isotopes, carbon-12, and then carbon-13 with an extra neutron, and carbon-14 with an extra 2 neutrons. And that's the guy we're looking for. So as we bend that beam, the lighter isotope, carbon-12, bends the most, carbon-13 likewise, but carbon-14 continues on, straight on down that pipe. So we're going to now count, we're going to measure the strength of the carbon-12 and the carbon-13 beams. But carbon-14 is a very weak beam, and we can't measure its strength with current. We have to actually count the atoms of carbon in that beam. So at the very end, we have a detector filled with a gas, isobutane, and the carbon-14 atoms come down and collide with those with the isobutane, and they give off their energy. So this is a high-speed collision. All that energy is dissipated, and each time there's a collision, we measure that energy. So now we come up with a count, and the number of carbon atoms is compared to the carbon-12 that we measured, and that tells us the concentration.
Okay, I unmuted us. Whatever one thinks, to me, that was just really cool.
It's really cool tech for sure.
Yeah, really, really cool. So the reason I put that on the table is how many, you could see that they could actually count individual carbon-14 nuclei.
Mm-hmm.
That's my understanding. They have a counter there. Now, I did a back of the envelope estimate, and I said, okay, what's the error? Well, depending on if they had an error in, they obviously don't count the number of carbon-12 atoms. But since there's, one would presume that if you just measure the weight, if you're off by 1% or 2, the count of carbon-14 nuclei would be off by 1% or 2 of whatever trace amount you had. So if you said the trace amount was 5%, it'd be 1% of 5% error if that was your measurement. I mean, we can work through the math, but
so
I think
the thing to remember is that you don't need much error. When you get down to very, very old dates, a very tiny amount of error is going to translate to a large amount of age, right? A great paper for this is Misunderstandings Concerning the Significance of AMS Background C14 Measurements by Taylor, Suthan, and Santos. And that was published in Radiocarbon in 2018. And you can get this, just Google it up. I'm pretty sure it's free. I have a copy. And they wrote a whole paper talking about what are the error sources in AMS dating, what causes them, and what kind of magnitude they have specifically because of this conversation. So they do, it's 23 pages. It's very readable. Highly recommended if anyone is interested in carbon-14 datings and the whole, is there carbon, can that explain diamonds and stuff? That's a great source to go check out. one
If
possible.
you could send that to me, I think
Yeah, I
I've
can do that.
actually read it, and you know, thank you for that reference again. If you could.
Thanks,
And by the way, if someone has a link to the rate book, Russell Humphreys sent me a link to it, and I've since lost it, and I should have downloaded it when I had the chance.
I think that you can just Google it and find it.
Right.
I'm pretty sure that's what I did.
But I will tell you one thing, that all the stuff that I've read on this, they said the diamonds should be blank, and they're not. Therefore, there's an error. I was having issues with them actually saying, okay, is there a problem with us counting? So one way to resolve this is if we could actually build a pure carbon-12 blank and then run it through this. And I've heard rumors that someone is trying to do exactly that, a carbon-12 blank. And I wanted to say, why don't you just collect the carbon-12 in your AMS and rerun it? And if someone's willing to finance that, we could settle this. So again, we have, okay, this is
they do blanks. I mean, they have blanks to recalibrate their machines. Like, that's something they do, and those come with a non-zero measurement. Like, that's how they like calibrate. You know, like this is 0. Put it in. What do we get?
How did they? No, I mean, not to be anal. How did they determine it was 0?
So
did they put it through an AMS first and then collect?
Well, that
you see what I'm saying is because you have those 2 lanes, you have something that's actually collecting all the carbon-12. That's the purest blank you could possibly have. Why don't they rerun it again? That's what I was saying.
So I don't think it's as simple as scooping up the carbon-12 and then saying that's a blank. I don't. I'm not a geochemist. I don't know. But
no. This is an important question, because the young Earth community, we've been in a discussion. We've said you're not going to find any blanks because they don't exist in the world. That's an assumption that you can find it in the. You can find blank carbon naturally. That was a mistake that the physicists made when they were trying to do the Boxerino experiment. They're trying to. The paleontologist said the coal should be blank. They dug it up and they said it wasn't, and then they came up with the explanation of radioactive sources. So I'm just saying this is a conversation I've had kind of floating around, is we actually have to manufacture a blank and then rerun it. And I don't know that anyone's figured out how we're going to get a blank. But I interrupted you, Jordan.
Well,
go ahead.
Even aside from that, you've got other sources of error, like contamination from other samples that you've run through the machine before, or even at the same time. You've got the fact that when it is bending that ray, what it is measuring is what is something with a mass of 12, what is something with a mass of 13, what is something with a mass of 14. But carbon-14 is not the only thing with a mass of 14, right? Now, they have measures in place to try to negate things like nitrogen-14 and stuff like that, like to avoid that from being a significant source of error. So they're aware of it and they mitigate it as best they can. They probably do a very good job. But again, that's a possible source of error.
And again, so, there's no point arguing over here. The way it'll be settled is what sort of experiments and procedures could we establish this. So the young Earth community is saying that we feel that kind of the explanations were too pessimistic, because it tends to be that they'd assumed diamonds, they wanted to use the diamonds as a blank, and it was returning figures from, I've heard as low as 30,000 years all the way up to 80,000. I'm just like, that doesn't make, I mean, I had issues with that. So, and even the Geiger counter could pick up to about 30,000. So I guess this is going to be, I'm just going to have to say, I don't think it's, as far as the young Earth creationists are concerned, we're going to keep trying to hammer on that end. I do know that if someone is a rich patron, and we have some very senior young Earth creationist physicists, they're interested in developing a blank and running it through an AMS machine. And we would be very curious how many counts. We don't want, when we send it off to the lab, sometimes they'll return a radiometric date. We would rather they just tell us how many C14 counts did you get. You could actually tell in this AMS machine, they can count how many C14 nuclei has passed through their system. If there's another source, that's fine. But just give us the count of how many things are passing through your system. And
so
yeah.
One question I've had, like, the creationist idea is that the C14 existed when it was created, right? For whatever reason.
Or C14, we may not know the mechanism for where some of the C14 came from, like in the coals. And that's why I'm interested in transmutation, obviously. And then also the neutron issue. And you gave me an interesting data point, by the way. Coal has graphite in it. Is it in the graphite form? Geologists help us somewhere. Wouldn't that be a nice way to slow?
I don't think so. But dude, I don't know.
Okay, so covert cuttlefish. So you just said graphite's a nice way to slow down very fast neutrons.
Mm-hmm.
I don't know if you could slow it down from like in the mega electron volt range down to a thermalized neutron. But
well, so for the purpose of moderation, I don't think it would matter much whether it was graphite or some other form of carbon,
okay.
Because, well, I mean, it might matter because you might lose some efficiency because maybe it has a longer mean free path through certain atomic structure, the crystal lattice, I don't know. But for the purposes of like a neutron hits a carbon atom, it doesn't matter what lattice that carbon atom is in, I don't think. I don't think, maybe. I don't think it does. But like, for whatever reason, it seems like when creationists point to the carbon-14 thing, the ages are always in the 30 to 80 or further range, right? My question is, which I understand, if in fact the carbon-14 is really there and there's no other explanation for it, that would be a big problem. I get it. But why is it that it's always so old? Like, why is there always so little? If it was just made and God could have made it with anything, why only this tiny bit, you know?
Okay, I'm going to address that. It's possible you misheard, or a creationist actually misspoke, or actually just said something that's unfactual or not accepted by other creationists. The consensus view is that there was little to no carbon-14 when God created everything.
Okay.
That's a theological statement, right? Okay, so just take it for what it is. But then the cosmic rays, and now we're realizing lightning could actually be a source of carbon-14. So when Adam sinned, that's when carbon-14 started to be added to the atmosphere. So for that 1,000 years, the carbon-14 was starting to accumulate in the atmosphere, and living things were taking it. So even though the carbon-14 dates are registering at 24 to 50,000, that's assuming that the carbon-14 that the creatures were exposed to is at today's level. When we adjust it for that, we start to get these older dates. I mean, we would get, and there's some evidence from archaeological finds. Bryant, he's Bryant Wood or something. He's a famous biblical archaeologist. He had dated the Jericho findings, and he mentioned that the C14 dates didn't agree, except we're finding other archaeological finds that would suggest that the C14 in the atmosphere was a little bit less than it is today. That's consistent with the theological view.
The amount of C14 in the atmosphere varies over time. That's why they have a calibration curve.
Right, but it was significant enough that we were able to get kind of a systemic thing with archaeological finds. It was actually increasing. Again, from the point of creation, there was not as much C14, and then it started to get added over like the next 1,000 years, even through Noah's flood. Young Earth creationists don't talk about it that much, but I'm going to show you a graph, a an Excel spreadsheet here, and correct me if I made a math error here. So let me, and it's talking about the percentages that we would be dealing with. So if we have, let's say 0 years, we should have 100% modern carbon. And I'm just going to use the word percent.
Sure.
Modern carbon.
Okay.
So at 5,730 years, we expect 50%. Is that
Yep.
correct?
1 half-life equals half the C14.
So this is how I calculated it. I used this function called power 0.5 raised to whatever number of cycles here. Cell C3 here. So for 30,000 years, we should have a residue of 2.65%. To me, I think an AMS ought to be able to detect 2.65%. And the reason I'm using that number, or even this amount, let me see. Brian Thomas gave his figure here for collagen, and I'm just saying, okay, I'm just trying to convey why we as young Earth creationists think, from an evidential standpoint, that the debate hasn't been settled yet, and that's why I wanted to go through this this discussion, because I'm not trying to say, okay, we're going to settle it today, but I wanted to say this is at least why some of us think it's not a done deal.
Let me share my screen real quick. There's a great graph in that paper I talked about that is this exact thing.
Okay, let me stop sharing, and you go ahead. I think when you share, I'll enable it as soon as I can, as soon as I see it. All right, here you go.
So this graph is basically what you were just saying. You can see this is the years, the apparent age of carbon, the carbon-14 age, about 1 half-life. You can see it's at 50%. So that's the same curve. If you just plotted out the formula you did, this is what you'd get. And just for because exponential curves can be challenging for dumb meat-brained humans like me to really like internalize, this is what it looks like. At 30,000 years, this is the percent modern carbon you'd have. Then you get to 40, 50, 60. You can see you're getting to extremely trace amounts as you get further past 30 and 40, 50,000 years. So it's not a trivial task to differentiate these kind of results from the noise you're going to get from error. And there's a active and continuous effort to reduce those errors further so we can push that age, that we can measure things further back, because that would be super helpful, but it's not easy.
So you feel my calculation was correct? Because sometimes okay,
it's definitely correct.
All right, so guys, this is, this a lot hinges on the C14, but I'll tell you why my suspicions were there. The chemists, like Dr. James Carter, who's been on my channel, also said the chemical dates align with the carbon dates as far as indications of youth. Racemization dating, oxidation dating, chemistry. We've heard about the soft tissue, but that's not at the chemical level. That's kind of like, oh, wow, it shouldn't be, it should be decayed by now. But I'm just throwing it out there. That's so people ask, why am I young Earth creationist? That's one of the reasons. There are other things that I find problematic, like even with solar system evolution, and that's a whole nother discussion. Because when I, just before I went to graduate school, I was reading books, the book Solar System Evolution, and the nebular, the hypothesis of gravity attracting all the particles and making a rotating disk, and then also the planets. It's not well known that trying to make a planet from a rotating disk is pretty hard. You can imagine gravity consolidating into a ball like the sun, but to have a disk around it that also becomes planets is actually very, very problematic. That was my beginning to change. So we've said right now there's concern for the precision of the precision and accuracy. What are the limits of accelerator mass spectrometry and the sources of error? But I will point out, this is where it'd be nice to have Erica on here. She could tell me, well, what dates are acceptable to the primate community when they're doing, if they use, to the extent they've used C14 dating, what are the outer limits for you guys?
I can tell you, according to the paper, which is written by people who do this, 50,000 years is widely accepted as you can't, further than that, it's meaningless.
How about earlier?
Earlier,
40,000. So 40,000 would give you a figure. Oh, go on. I'm sorry, I interrupted you.
So I know past 50,000 years is basically verboten. That, with our current technology and techniques, that's not going to work. And then as you come down from 50,000, the further you are from there, the more confident you can be, because your sources of error are going to be small in comparison to a large amount of modern carbon, if that makes sense. But the smaller your amount of modern carbon gets, so when you get into 40, 45, 48, the closer you approach that threshold, the less certain you're going to be.
So I have Brian Thomas's paper here where they did a collagen extraction and then they purified the collagen out of the dinosaur bone. And it had 5% modern carbon. I don't have the, he had another table here. See if he had one. I think it's page 2. I just kind of pulled this up now and it's been a while. Okay, so there was one here. Okay, so there was a collagen here and you could see the numbers. He had one with 5.59%, a hadrosaur femur. And when they can extract the collagen, I think the highest number they had, I have to talk to Dr. Thomas, or someone would recognize some of these names. So what they did is they went through a gelatinization process where they can extract just the collagen. So it would be free from contaminants because bacteria don't make collagen, neither do fungi. So if they subjected the bones to weak acid and they extracted the collagen, that stuff is definitely from the dinosaur. And then when you have just the pure collagen, it's that protein there. It doesn't have any added, you can presume that there's not really significant amounts of other contaminants. So the figure that he had that I drew up here is 1.64%. And I'm going to just approximate and see 1.64. That'd be about 35,000 years. 34,000, see. Yeah. He got a date of 34,000, which I think is within also even the Geiger counter range. What I should have asked Brian Thomas is, did you run a Geiger counter test on this? The Geiger counter, I think, will count to about 30,000 years. So I don't think, so he said we need to dig up more bones. We need to find more samples. And again, this is where I've been. I think it's worth a discussion. Is 1.64%. Is even okay? So he has one here that is a collagen of 0.57%. So let me see if I can get 0.57%. That would be
somewhere around 42,000.
Yeah. Somewhere around that. Anywhere, somewhere 43,000. So
so for me, if I'm looking at it as a good Bayesian, like I am. If I have two possible explanations for this observation. Say it's 35,000 years old, whatever that translates to percent modern carbon. I can either accept that every interconnected field of science is wrong, and we need to upend our entire scientific understanding, flip the table, and start over, or there's a source of error. Error is something we know can happen. Contamination is something that is a known thing that can exist, and that's what caused it. If I'm looking at those two options, option B has a way higher prior than option A. And so I'm going to need a lot more than a few anomalous readings in order to be willing to accept that this is in fact not error. This is, and it's not something de novo that's being created in the ground. And like eliminating all of that would be necessary before I'd be willing to even entertain that this is evidence that like this huge mountain of evidence is also wrong. You know what I mean?
Oh, and that's totally fair. That's kind of where we're having to leave it right now. About the only thing I think we can really agree on is I think there's going to be frontiers of research in nuclear physics from practical applications that may be relevant to what we're doing. So I really do hope that the clean energy, I know someone corrected me, the word green energy has other connotations, because it tends to be solar and wind, and not everyone's on board with that. I'd like the clean fusion or clean low energy nuclear reactions. And that might be where we leave it. I will point this out. There's one other paper here. And I'll put this in the video description. I hate Reddit. I had an article, and I'll just briefly cover it. And I'm sorry the font is so small, but I'll read it here. I'll put in the video description this journal, that link you see there in the blue, from journals, University of Arizona on radiocarbon. Said many C14 dating laboratories have established that coal samples exhibit a finite C14 age, apparently caused by contamination of the specimens before any laboratory preparation is undertaken. That's the opinion of the author. Because coal is formed over geological timescales at depths providing excellent shielding from cosmic rays, its C14 content should be insignificant in comparison to the C14 introduced by even the most careful sample preparation techniques used in C14 laboratories. How then is it that a material which should show a C14 age indistinguishable from that produced by a combination of machine background and contamination during careful sample preparation routinely produces a finite C14 age? One suggestion is that radium, which is present in some coals at the sub-PM level as a decay product of the uranium-thorium series, may produce C14 during extremely rare decay events. And he cites more. They've detected the C14 from this process in uranium-thorium ores, and he keeps citing. But he said, thus the amount of C14 produced by such events derived from radium and coal must be considered as insignificant. And then the creationists have tried to evaluate the various kinds of decay chains that could make C14, and they came up with this similar conclusion. I'll try to make a link to this paper by Rada that covers it. Unfortunately, all the terms in this paper I really didn't understand. But
I understood most of them. If you want me to talk about them, I understood most of them. If you want me to talk about them, I did read it.
Actually, could you help me read through it? This I mean, not today, because this is a big paper. It'd be educational for me and others. And then there was another one. Jay Weil wrote me just a personal letter. I wanted something public domain, so I'm presuming there wasn't anything that was like really secret.
Yeah, he made a pretty big error in there, though.
Okay, all right. You may have saved me. See, this is why I wanted to have you work through this on the channel. If he made an error, I think it's important that it be corrected. And if his calculations are wrong. The reason I was leaning toward it being, he may have arrived at the correct answer for the wrong reasons, is because of that other paper that I just read, and we can cover that. But since we're already at about an hour 30 mark, maybe we could do this next week if you have time, and we could go through
Yeah, though I would, so for anyone who hasn't read the paper, basically, or Jay Weil's note was talking about C14. He made a mistake, but anyway, Rada is addressing the claim that uranium spontaneous fission could lead to the production of C14 in coal specifically, through the absorption in carbon-13 and primarily nitrogen, because nitrogen-14 absorbs a neutron and emits a proton and becomes carbon-14. That's what happens in the atmosphere, actually. So that's what he's addressing. His claim is the amount of uranium in coal is not sufficient to produce enough neutrons quickly enough to lead to the levels of carbon-14 we see. I want to check his math because I haven't had the opportunity to do that.
And I haven't, by the way, I haven't really read through the paper either. So,
it was published in 2003, and I looked, and nobody has addressed it, which means maybe I have to address it. I don't know.
No, this is, I think this is a good process for me to learn. And I didn't want to just, when I sprung this on you, it wasn't like, I wasn't going to get in your face and say, prove it or disprove it. I respect you enough that I just wanted to say, I just put this on the table, and we were going to figure out how we're going to get through this. And I also wanted to find out if you're interested in actually even reading through some of this stuff with me to help me learn. And maybe both of us can learn some of this, because if we could say, okay, certain things are off the table as far as mechanisms, that would at least move the conversation forward. We could say then, if there is an error, it's then another source of contamination, or it could be instrument error with the AMS system, or who knows what else. And we could talk about, bacterial contamination or stuff leaching in. So, I mean, the three major sources of error that I've heard so far are, contamination, instrument error, and then now radioactive sources. So if we could, I wouldn't say that we're going to eliminate all radioactive sources. Can we, just kind of say, it's not going to be this way, it's not going to be this way.
Sure. I'll say I actually didn't know until today that C14 could be emitted as part of the uranium decay chain. It literally never came up my entire schooling because it's so rare. It's such a non-issue that I didn't even know until today that was even a thing that happened.
Okay, well then I feel like I hope that was valuable then, that I gave you something. Okay.
I mean, it happens like 1 in a billion or more decays, so it's not really relevant for anything I'm ever going to do, but it is neat to know.
All right. And just to throw this out, guys, at some point I will throw some of the more kind of like fringe low energy nuclear stuff in a subsequent show. I'm not endorsing it at all at this point. I am saying what experiments will we have to run to make this believable, and that I'll leave it at that. I will say I continue to be astounded by the number of chemists in very expensive laboratories devoting a lot of time to this. So something is persuading them to pursue this. Unfortunately, I think there's also been a lot of cranks and also a lot of conspiracy theories surrounding this. But this is relevant to young Earth creationism, because as Jordan and I have actually agreed on something tonight, the claim of accelerated decay, it's like, young Earth creationists, you don't want to go there. I don't think you want to go there.
No.
Look for other avenues. I know you're eager to solve the problem, but you know, I will tell you this, if you're an abiogenesis researcher, you always have promissory notes. So if it works for them, it can work for us.
So you want to hit Rada and them another time? Do you want to see if anybody in the audience has questions before we?
Yeah, we could actually, I would like to go through Jay Wild's calculation and see how we can
Sure.
clean it up or correct it, because I actually understood that.
Yeah,
And
that error is pretty simple.
okay. And if we can eliminate it, it's like, okay, I won't use it. So
Sure.
this conversation has already been valuable to me. As I said, my audience are very sophisticated. A lot of them are grad students. They may not be in nuclear physics or physics, but they would appreciate what you have to say and what we're doing here. So did you have any closing thoughts?
So do you want to do the JWoww thing now or next time?
How about, would next time be
sure
more feasible? Because audience, I just want to say, I sprung all this on Jordan last night, and I said, don't devote a lot of time to it. I wanted to have a chance to have this conversation we're having now. So just in fairness to him, you know, I didn't want to force this on him, and you know, maybe he can, even though I'm sure he could help us with the JWoww thing, if you wanted to have a little more time to, if you like doing PowerPoints, which I like doing for myself, if you wanted to do anything like that.
Sure.
And I wouldn't necessarily put a lot of time into this, because actually this show is kind of our chance to actually do it on the fly, and people can see what it's like to be a student of science and struggle through this.
Well, there's no way I'm going to do intense nuclear calculations on the fly, but but so if I'm gonna try to legit address the points that Rhoda makes up, I'm gonna need to pull out my calculator and do some work. I can't guarantee I'll do that in a week, but it is now.
That's fine, because you're doing
now on the list of things that I want to do eventually, with a great many other things. Hopefully, I'll get to it.
Well, you know, you're doing this as a free service to humanity here. I can only ask so much, but you're the first guy that's willing to actually look at some of this with me and walk through it, even as far as we've gone, you know. So,
well, like I said last time, I used to be a young Earth creationist, and the reason I do any of this at all is because I want to reach me from like 15 years ago, basically. I want to have conversations that I wish I had heard back when I was a young Earth creationist and understood, so I could better understand what the actual science said, and even more importantly, what questions to ask, how to ask them, and how to find the answers. You know.
And if I could say this, I didn't go through a deconstruction, because I didn't start out as a young Earth creationist. I was where you are now. And what I was spared from was the feeling that I was lied to by the community. And one reason I didn't pay attention to most of them, because I could tell a lot of the stuff they're saying was wrong. And the reason I can say that even more emphatically now is they themselves are rejecting their old arguments. I'll give you an example. We talked about C14. About 20 years ago, I still saw a lot of young Earth creationist articles saying C14 is just terribly unreliable. Can't trust it. Boy, how the tune has changed in 20 years. It's like, now that's the best thing since sliced bread. This is saving young Earth creationism. And so where you were 15 years ago was about where I was seeing a lot of the garbage in the young Earth community, but I was starting to see like little pockets of like sanity. And I know that may sound harsh, but how can I say that? Well, looking in retrospect, the young Earth creationists have done a 180 on radiometric dating for C14. They haven't done a 180 on other things. But it's just like so funny. You go back 20 years, they were rejecting racemization dating. They were rejecting carbon-14 dating and saying, look at all the errors and unreliability. It's like how times have changed. And so I could sympathize with the feeling that we were getting getting the raw deal, because the arguments back then were not good, and even like the second law thermodynamic stuff, which is they're saying that's evidence against abiogenesis and evolution. I'm just like, I studied thermodynamics, so I could see how people could get deconstructed and just fed up with it, because the popular stuff actually, I think, is damaging. And that's why when I run this channel, I have a different approach. I'm going to say, guys, there are severe problems with this. Don't trust the popular stuff, because it's not as good as they say. And privately, some young Earth creationist researchers said that the popularizers are telling you a different story. It's not as good as what they say. And so you could either decide to be a young Earth creationist, some sort of old Earth person, or you say, I'm undecided. There are three options. Being undecided, I think, is fine.
I don't know. It's always a possible answer to any question.
Yeah, and so that's why I run this channel differently. It's like, if Jordan says there's an error in J. Wild's calculation, I'm going to say, let's look at it, and I'll say thank you. Other channels will just kind of change the subject and try to demonize him and argue and do a lot of dishonest debate tactics. That's not, that would be irresponsible of me. So that's a long way of saying I'm glad we can actually finally have this conversation that you wish you had 15 years ago. So anyway, if you had any final words, I've talked too much actually.
No, thanks for having me on. I always enjoy talking radioactivity and nuclear stuff. Like I often say, I'll talk to literally anyone about it at any time for any reason. So if anyone is interested in hearing me talk about other stuff, you can check out my podcast, and we're also on YouTube. We don't just talk religion and young Earth creationism. We talk about a wide variety of stuff: alien abductions, Bigfoot, the Illuminati, whatever, anything related to skepticism. And like I said last time, we don't see being religious and being skeptical as two opposed things. I think anybody could be a skeptic. Like any worldview can incorporate some skepticism, and I think if the world was full of more skeptics, it'd be a better place. So
yes. So I'll see you backstage, and Dustin, you said it all. Much love, and thank you for that. I'd like to thank everyone who's watched us, and I'll see you backstage briefly. I have the links to Jordan's podcast and channel or website in the video description. I'm going to add some more stuff to the video description, and Lord willing, we'll see you hopefully next week. Take care.
Cool.